Okay, can folks in the chat hear me on Zoom? Wonderful. Okay. Let me actually bring this back up. Hello. Oh, I have to do that. Oh, it's not projecting up here. How do I do this? Gotta be kidding me. A little louder. Oh, maybe not. Let me take a look. That go away. Security. I don't know where to set that. I will just try to keep on top of letting people in, if you can. All right. Now, why Samsung Digital Presenter? Samsung, so that's right. This is going to be really hard to do if we don't have a document camera. Would you be able to run over to the help desk and tell them we can't get the document camera? Yes. Oh, wait. Hold on. Aha. Huh, but apparently it's backwards on the on Zoom. Oh, okay. That's what it is. Okay. Okay, I apologize for the continued technical difficulties. Seems like we are now up and running better. Remember that every time we come in here, we need to do the seating survey. So please log in and do that. This is section 3, and put in your seat number. Just as a reminder, the upcoming deadlines we have today at 5 o'clock, the entry surveys needs to be done. This one is really critical so that I can assign you to a small working group that has the same schedule as you. The syllabus scavenger hunt is due, and the week 1 video quizzes are due today at 5. On Friday, the homework one is due at 5 o'clock, and then the first small group activity is due next Tuesday. So with luck, I will tomorrow be able to have you assigned to your groups, and you'll be able to coordinate before the weekend when you're going to work with your groups on that activity. Okay. Are there any logistical questions before we get going on the material for today? Anybody here? Anybody on chat? Nope. Okay. So I took a look at the muddiest point list on Piazza, and we have quite a few that are pretty good. So I'm going to start by going down those. The one that got the most votes was about dipole interactions, and are the attractions and the repulsions always equal to each other? So does anybody have any thoughts on this particular question? Yes. Right, there are going to be rearrangements that happen. And so if we, what is the law that determines the forces? Anybody remember that? Yes. Coulomb's law, right. Where the force is equal to Coulomb's constant times charge 1 times charge 2 over r squared. Now, if the two charges are the same, but just different signs, in the case of attractions and repulsions, and if the distances are the same, then the force will be the same. But when you have an attraction and a repulsion, that typically applies a twisting force, a torque, because they're located in different places, which means that the R's are not going to stay the same as long as the molecules have an opportunity to rearrange themselves. And so when they rearrange themselves, if you have, say, a positive charge here, and you have a dipole here, where the two ends are starting out at the same distance, here we have a repulsion, here we have an attraction, and so that provides a torque. And so the molecule will then rotate, so the negative end is here and the positive end is here. And now that this distance to the negative end is smaller than this distance to the positive end, the attraction dominates over the repulsion. Does that generally make some sense? Okay. Now, there's nothing inherent about a dipole that says that this is the case. So if, for example, you somehow have the molecule fixed in place so it cannot rotate, then yes, the attractions and the repulsions could balance out, could be equal. Also, if the molecule is a long way away, then the forces are both pretty small, and so the torque being applied may be smaller than the random motions of the molecules in space. So there's nothing intrinsic about it that makes them unequal. It's just that when the molecule does have a chance to rearrange, it will do so. Okay, does that generally make some sense? Any follow-up questions on this concept? Okay. Yes. Right, so the question from the chat is a larger R squared is weaker. So the idea here is because it's in the denominator, if R squared is larger, then being in the denominator, that makes the force smaller. So just as an example, suppose R is 2, so you have 1/4, but then suppose, and then compare that to R being 3, it would be 1/9, and 1/9 is a lot smaller than 1/4. Okay, so moving on from that, so let's stick for the moment with the intermolecular forces part, and we'll come to the phase changes and stuff on that in a little bit. So we have a question here on hydrogen bonding requiring donor and an acceptor. And I see some nods from the class here. That is correct. Hydrogen bonding does require both donors and acceptors. Let's look at an implication of this. So I think the example we looked at was oxygen with hydrogens, carbon and hydrogens coming off of it. This is dimethyl ether. And so remember our model for a hydrogen bond. It has to have a hydrogen, that's part of it. It is attached to an element X, and it is hydrogen bonding to an element Y that has a lone pair. What has to be true about X? Yes? Almost. Anybody want to? Yes? Nitrogen, oxygen, or carbon? Yes? Nitrogen, oxygen, and fluorine. Yes. So nitrogen, oxygen, or fluorine. If we look at the periodic table here, remember that the electronegativity goes up as we go towards the upper right portion of the periodic table. And we don't have to consider the noble gases because electronegativity is about covalent bonding. So the elements that have the element with the greatest electronegativity is fluorine, then you have oxygen, then you have nitrogen. Carbon is also relatively electronegative, but it seems experimentally to be below the threshold for being able to cause a hydrogen bond. Okay, so the three most electronegative elements are the ones that we care about here. What has to be true about Y in this model? Anyone? Yes. It does have to have a lone pair. Can it be anything with a lone pair? No? Okay. Yes? From the chat? Has to be small. Okay, so let's look at the periodic table again. Where are the smallest elements? The top. Okay. Let's say this period 2, so the lithium through neon period. Which of those have lone pairs when they bond? Say it a little louder. Nitrogen? Carbon. Carbon has lone pairs when it bonds. So let's think about that. And a good way to think about this kind of problem is to think about it bonding with hydrogens. Okay, so carbon, how many valence electrons do we have? We look at the periodic table. Okay. 4, correct. So 1, 2, 3, 4. We're going to bond with hydrogens until we complete our octets. So we're bringing in a hydrogen with 1, hydrogen with one, hydrogen with one, hydrogen with one. We now have an octet. The hydrogens have their duet full, so this becomes the carbon-hydrogen compound that we have. Do we have any lone pairs? No, we do not. Okay. So in order to have lone pairs, let's move over to the nitrogen case. How many valence electrons do we have for nitrogen? 5, correct. So 1, 2, 3, 4, 5. Start bringing in hydrogens. Hydrogen with 1, hydrogen with 1, hydrogen with 1, and now all of the atoms have completed octets. Does nitrogen have a lone pair? Yes. Okay. So seeing that trend, which elements in period 2 are likely to have lone pairs? Nitrogen, oxygen, and fluorine, exactly. And so it turns out that element Y here has exactly the same set of allowed elements as element X, nitrogen, oxygen, and fluorine. So for a hydrogen bond, both the element that the hydrogen is covalently bound to and the element providing the lone pair have to be a nitrogen, oxygen, or fluorine. Okay? All right, now let's come back up to this. So can this molecule hydrogen bond to another of the same type of molecule? I see a couple of heads shaking. Why not? Okay. Anybody like to? Yes. Right. So in order for something to be a hydrogen bond donor, the hydrogen has to be attached to nitrogen, oxygen, or fluorine. And all of these hydrogens are instead attached to carbon. So even though there's an oxygen with lone pairs on here, which can be a hydrogen bond acceptor, there is nothing on this molecule that could be a hydrogen bond donor. Now, let's extend this a little bit further and imagine that we are now taking this molecule, dimethyl ether, and we are mixing it in a solution of ethanol. Okay, is that visible? All right. So let's suppose we now have these two molecules that are together. Can there be hydrogen bonding between those two molecules? Yes, it can. So this hydrogen here can act as a hydrogen bond donor, and these electron pairs here can act as hydrogen bond acceptors. So ethanol and dimethyl ether can hydrogen bond to each other. So we should be able to make a prediction from this. Should ethanol and dimethyl ether be miscible, meaning that can they mix together to form a solution? I'm seeing a few nods, and that's correct, because the solute-solvent interactions are strong. And so those solute-solvent attractions allow the molecules to mix. And in fact, experimentally, we find that these two molecules do form a solution with each other. Okay. All right, any other questions on hydrogen bonding in general? Nothing from the chat. Okay. All right. We've done this one. Okay. Melting points in decreasing order among ethanol, dimethyl ether, oxygen, and lithium fluoride. Okay. So the first place to start with most of these is going to be with drawing their Lewis structure. And both ethanol and dimethyl ether were molecules that were used as examples in the Intermolecular Forces video. So you should have had access to those Lewis structures. So this is ethanol. This is dimethyl ether. Oxygen, I hope you learned last semester, is a diatomic molecule. And then lithium fluoride is an ionic compound. Okay. So, what general principle, get that up high enough. What general principles are we going to be thinking about as we try to evaluate their relative, do we say boiling points or melting points? Melting points. What general principles are we going to be looking at? Yes, from the chat. Intermolecular forces. So what is it about intermolecular forces that's going to determine this? Do we want high intermolecular forces for a high melting point, or do we want low intermolecular forces for a high melting point? Yes, we want high intermolecular forces for a high melting point. That's correct. So one of the best places to start would be to go down through each of these and identify what intermolecular forces are present. Okay, so let's start at the top. What do we have in the case of ethanol? There is one type that is always present. Anybody know what that is? Yes. Dispersion forces. So London dispersion forces, also known as induced dipole forces. So we have dispersion forces, and I just said that's the one that's always present, so we're going to have that in all of these. All right. What else are we going to have? Yes. Hydrogen bonding in the case of ethanol, that's correct. Okay. Do any of the others have hydrogen bonding? No, I'm seeing some shaking of heads. That's correct. None of the others do. Okay, what's the next one we want to talk about? Is there anything else in ethanol? Something from the chat? Okay, so polarity is the closest of those answers. When we talk about something being polar, what kind of interactions are we talking about? Yes. Attractions and repulsions, but when we list the type of interaction, when you have a polar thing, yes? Okay, well, we will get to electronegativity in a moment because it does play into this. It comes into determining how polar something is. So that's a good thought, yes? Dipole. So if something is polar, because it has two ends of different polarity, we call it a dipole. And so what we are looking at is a dipole-dipole interaction. We will definitely come back to the relationship to electronegativity in a minute, okay? Because one of the big questions is, how do you tell if something is polar or not? And so we'll We will come back to that. Do any of these other molecules have dipole-dipole interactions? Yes. Not really. So the question was, does lithium fluoride have dipole-dipole interactions? And not really, because we treat the lithium and the fluorine as separate. So they are electrical monopoles. So they have a different kind of interaction. Do you remember what that's called? Ion-ion interactions, yes. And that is the only one of these that has ion-ion interactions because there's nothing else that is charged here, okay? So let's think about the dimethyl ether for a moment. And I want you to think back to last semester's work on valence shell electron pair repulsion theory when you talked about geometries of molecules, okay? What is the geometry around the oxygen? How many electron domains do we have? 4 electron domains. What geometry do 4 electron domains adopt as they try to get away from each other? Is that a hand back there? Okay. Yes. Tetrahedral, that's correct. So we'll come back to this. Tetrahedral, remember, has your central atom, one coming up, something coming out towards you, one going back in, one going here. Now, in dimethyl ether, this oxygen, 2 of those are lone pairs, and 2 of them are covalent bonds. So let's say we've got a lone pair here and a lone pair here, and then this goes off to a carbon, this goes off to a carbon. So is the oxygen-carbon bond polar? Yes. Does the geometry allow those polar bonds to cancel out their effects? I see a nod. I see a shake. So which is more electronegative, the oxygen or the carbon? The oxygen. So that means there's going to be more negative charge on the oxygen. So if we draw the dipole arrow for this bond, it looks like that. If we draw the dipole arrow for this bond, it looks like that. Are they pointing directly towards each other? No. Which means that the oxygen end of the molecule is going to be slightly negative, and the carbon ends of the molecule are going to be slightly positive. So this does have a dipole. It may not be a very strong one, but it has a dipole. So dipole, dipole. Okay. Are there any other interactions we need to think about? Let's try to get all that on here. Yes. It can. So the question was, does the size of the molecule matter when it comes to melting point? And yes, it can. And we will go into some details of that in a little bit. I'm going to make some notes here. We want to come back to electronegativity, and we want to come back to size of molecule. There are a couple of different ways that can have an effect. But yes, we'll come back to that. Yes. Okay, so the question is the difference between an ion-dipole interaction and an ion-induced dipole interaction. Did I state that correctly? Okay, so when we're listing the types of interactions, if we say a dipole, then that means a permanent dipole. That means something that has the separation of charge built into the structure of the molecule. So ethanol and dimethyl ether here both have permanent dipoles. An induced dipole is where you take something that has a that has electrons, which basically means anything we're talking about other than an H+ ion. You take anything that has electrons, and you bring a charge or a dipole or something like that up next to it, and that polarizes the electron cloud. So the thing you bring up next to it induces a dipole into the electron cloud. So anytime you can have an induced dipole on something that has a permanent dipole, which basically just makes the dipole stronger. You can have an induced dipole on something that doesn't have a dipole moment. So you could bring a charge or a dipole up against a noble gas, for example, and that would polarize it and induce a dipole in it. So does that help? Okay. With that in mind, with induced dipole being brought up, are there any induced dipole interactions in any of these, other than dispersion, which we described as induced dipole, induced dipole? So let's see. Ethanol, does it have any electrons? Yes. Okay. So if there is something that can induce a dipole, it will be able to. Is there something that can induce a dipole in this? It is itself a dipole. So that's bringing up charges, separated charges towards a set of electrons. So yes, so this can have a dipole, induced dipole interaction. Okay. How about dimethyl ether based on that? Should this have a dipole, induced dipole interactions? Yes. Okay. Oxygen. Does this have a dipole? No. Does it have separated charges like ions? No. So other than induced dipole interactions, does oxygen have any kind of induced dipole interactions? No. Okay, so we're done with oxygen. Now, what about down in lithium fluoride? What kind of, are there any induced dipole interactions we can have here? I see a nod. I see some blank stares. Do lithium and fluorine have some electrons? Yes. Lithium and fluorine are separated charges, so you're bringing charges up against electrons. Can that induce a dipole? Yes. So ion-induced dipole interactions. And here we have our full list of the types of intermolecular forces that we're dealing with. Which of these has the weakest intermolecular forces? Oxygen, correct. So we would expect oxygen to have the lowest melting point, which kind of goes with our expectations because oxygen is a gas, right? So lowest melting point. Okay. Which of these is next lowest, has the next weakest set of interactions? Yes. A little louder? Lithium fluoride. So this is suggesting that the ion-ion interactions would be weaker than the dipole-dipole interactions and the hydrogen bonding and so on, if that were true. What do people think about that idea? Yes. they would be the strongest. So if you think about most salts, most ionic compounds, they are solid crystalline substances. And that is because they have the strongest type of interactions that you can have. So this one is going to be the highest melting point. In fact, can you do a quick Google search and find out what the melting point for lithium fluoride is? That would be really cool to know. Okay, so ethanol and dimethyl ether are in between. Which of those has stronger interactions? Stronger intermolecular forces? Yes. Ethanol, why? Hydrogen bonding, that's right. So, so the order going from lowest to highest is going to be oxygen, dimethyl ether, ethanol, lithium fluoride. I don't remember in the question whether I said go lowest to highest or highest to lowest, but that's the order from lowest to highest. Yes.
Melting point for lithium fluoride is 848 degrees Celsius.
Yeah, that's just crazy. 848 degrees Celsius. I just remembered something. Quick break from the content. You wanted to announce your LA sessions.
Oh, yeah.
Sure.
Okay, so today is our first LA session at 1:30 over Zoom. We'll just be going over this week's content, and then that'll be it. There's also another LA session on Friday if you can't make it today. If you've never been to an LA session, it's kind of just like a study session. If you don't know me, I'm Brittany. I'm just a student like you guys, but I've taken this class before, and yes, I'm here to help.
Is Friday at 1:30 as well?
Friday is at noon, actually, and they're always going to be over Zoom. We're having no in-person LA sessions this semester, unfortunately.
And do you know your counterparts' session times?
I do not, but I
Okay.
can look them up.
I think she posted them on Piazza. So
Did she?
I think so.
Okay.
So I will collect those two together and I will post it to Piazza as well.
Okay. My last session time is on Sunday. I want to say, I can't remember exactly. I think it's around 6 o'clock.
I will verify that with you before I post it.
Okay.
Okay, thank you. Okay, so let's come back now to this. So we have answered the specific question about the melting points of these particular compounds, but a couple of other questions came up along the way. So why don't we continue on down that rabbit hole, and we'll explore a little bit more about the about intermolecular forces. The big thing I'm going to be looking at first is how do you tell when a molecule is polar? And we went over that a little bit in talking about the oxygen that we have here, but let's really focus in on that for a moment. So the first thing you have to know is how do you determine if a particular bond is polar or not? Because it's going to be the geometry of the bonds that's going to determine whether it's going to be, whether you're going to have an overall dipole moment. And it does come down to electronegativity. So electronegativity, can somebody give me a brief definition of what electronegativity means? Yes. How likely an atom is to attract electrons. Okay, that's a very good start to the definition. Anybody want to refine that a little bit? There's an extra component to electronegativities which sort of distinguishes it from electron affinity, which is kind of what you were describing. So electronegativity is specifically about bonding. And so it is the strength with which an atom attracts the electrons that are in bonds with it. Okay? And so, so what we do is we then look at, say, fluorine versus aluminum. So fluorine is extremely electronegative. Aluminum is not very electronegative. And that means that the fluorine is going to hold on to the electrons that are in its bonds more tightly. So if we have aluminum here and we have a fluorine here, then the electron cloud that you have is such that these two electrons are spending most of their time around the fluorine. So you have aluminum and then you've got the fluorine, and the electrons are zipping around over here and only occasionally coming over near the aluminum. Okay, does that make some general sense? And so what that means is that the fluorine adopts a partially negative charge and the aluminum here adopts a partially positive charge as a result of that. Because in order for them to both be neutral, the electrons would have to be shared equally between the two. Now, every pair of elements that you can form a bond with, if the elements are different, there is a difference in their electronegativities. It may be small, but there is a difference. So I personally consider it correct to say that if the elements are different, you have a polar bond. It just may be a very weakly polar bond. Most textbooks will give you a threshold difference, and they will say that if the electronegativity difference is less than, I think it's 0.4 on their scale, they will say that that is effectively a nonpolar bond. Question from the?
Dana from the chat wants to know if they'll be allowed a periodic table with electronegativities.
You will definitely be allowed a periodic table. I don't know if it's going to have electronegativities on it. I'm considering having the exam pretty much open resources so that you have access to anything you want. But I have not made that decision fully yet. So most textbooks will say that below 0.4 electronegativity difference, you treat the bond as nonpolar rather than polar, and above 0.4, it's treated as polar. I think that cutoff is a little bit arbitrary, especially since there are different electronegativity scales that could be used, where the numbers actually differ somewhat. So I'm never going to ask you a question that's going to be borderline. So you don't need to worry too much about that particular aspect. Now, we said that the carbon-oxygen bond, when we talked about ethanol and dimethyl ether up here, we said that that one was going to be polar. Well, if we look at carbon dioxide as an example, each of those bonds is polar. But is the molecule as a whole polar or not? So in order to get to that question, to find out if this molecule as a whole has a dipole moment, then we have to go to geometry. So let's look at our central atom, the carbon. How many electron domains do we have? 2. That's correct. This is one domain. This is a second domain. What is the geometry that 2 electron domains adopt around a central point when they're trying to get as far apart from each other as they can? Yes, linear. So that means that the way I've drawn this molecule here is in fact correct. The molecule is linear like it's drawn. And so if we put on here the dipole moments, this dipole moment for the right-hand side looks like that. This dipole moment for the left-hand side looks like that. They are equal and opposite. And so if you've ever done vector addition, so in a geometry class, you have a vector and you add another vector to it, and then you see what the resulting vector is. If you've got two vectors that are exactly opposite each other, they cancel out to 0. So carbon dioxide does not have a dipole moment. It is nonpolar. Okay. So that is the general procedure you go through to determine the whether a molecule is polar or not. You have to start with the Lewis structure. You then look at the bonds to determine which bonds are polar, and then you look at the geometry of those bonds to see if everything cancels out or not. Any question about that general idea, the idea of how to determine polarity in molecules? Yes? Doesn't symmetry have something to do with polarity? It can, because the more symmetrical a molecule is, the more likely that the molecule, that the dipole moments from the individual bonds will cancel out. So, for example, if we look at methane, which we looked at earlier, where did I do that? So I drew its Lewis structure like this. But does that accurately represent its geometry? No. What is its geometry? Yes, from the chat?
Brittany said tetrahedral.
Tetrahedral, which is correct. And so tetrahedral is completely symmetric, and if you do vector addition of the 4 bonds, they completely cancel out. What about ammonia? Ammonia has some symmetry, because if you look at its geometry, it's the electron domains are still in a tetrahedron. It still has some symmetry, and then because you can take the ammonia and then rotate it around the lone pair, and you find other arrangements that are identical as you do that. So it's symmetric in a sense, but all of these point such that you have the dipole moments pointing up towards the nitrogen, and the nitrogen is pushed up out of the plane of the hydrogens, right? So that means the nitrogen end is going to be negative and the hydrogen ends are going to be positive. Okay. All right, we doing okay on dipole moments now? All right. So, so that was the discussion about electronegativities. There was a great question that came up a moment ago about, doesn't the size of the molecule have an impact? And the answer to that is yes. And so let's talk a little bit about that. And we're going to talk about 2 aspects of it. So the first is, let's imagine going down the periodic table. So maybe we do something like methane, so carbon with 4 hydrogens around it. And you should hopefully know that within a group, you will frequently have similar bonding when you go down. So while we have CH4, we can have SiH4, we can have GeH4, and so on down. So going down the periodic table here, let me back up a minute. So methane, what are the intermolecular forces that we have in just pure methane, CH4? We just looked at the molecule a moment ago, it was the tetrahedron. London dispersion forces, and that's it. It's the only thing, it's a nonpolar molecule. As we go down the periodic table to silicon, to germanium, and so on, all you're doing is adding on more shells of electrons. More electrons means that it's now, that the electron cloud is now sloshier. There are more electrons around it, so an induced dipole that can be formed from it is higher, right? So if there are more electrons, if it's sloshier, then bringing in a charge next to it will cause a greater induced dipole. And so that's going to do things like increase the melting point, okay? And remember that London dispersion forces are just induced dipole interactions. So that what's happening is that the natural instantaneous sloshing of the electrons that around, the fluctuations in the electron positions, start to get in sync with each other. And the electrons are now dancing like a conga line with each other. And the more they're sloshing, the higher the kicks, I guess. I'm pushing the analogy a little too far. So one way to look at the question of size having an effect on intermolecular forces is that the bigger the molecule, the more electrons you have, and so the greater the induced dipoles you can get. Now, there's another way that size can have an effect, and it's also related a bit to shape. So let's imagine that we've got some kind of molecule that sort of in 3D space is kind of worm-like, okay? So we have carbons and hydrogens and oxygens and things all along in there. And we've got a couple of these molecules that come together, and they can now kind of nestle up next to each other so that there's a lot of surface area interactions. Remember that all of these interactions are at their base a result of Coulomb's law. Every one of the intermolecular forces is based on Coulomb's law. So the closer that each part of one molecule can get to another part of another molecule, the closer they can get, the stronger the attractions. Now, if we have another molecule that's the same size, has the same number of atoms in it, and even the same types of atoms, but if it's arranged in a way that's much more spherical, and you bring two of those up close to each other, the surface area of interaction is a lot lower as a result. Because here, we've got a lot of really close interactions. Here, we've got some close interactions here, but not much else, but they aren't very close in other locations. So this molecule here and this molecule here, even if they have the same types of interactions, this one will have stronger attractions because it's able to nestle up next to adjacent molecules much more closely. Does that generally make some sense? Okay. All right, how are we doing on time? We go to 11:40, right? Okay, so we got some time left. Okay, list of questions. Did this one. Okay, related to what we were just talking about here. Relative boiling points of water, ammonia, and hydrogen fluoride. And so the question that was asked was understanding why water has a higher boiling point than ammonia, but not so clear on why water has a higher boiling point than hydrogen fluoride. Okay, so let's look at those three sets of molecules and figure it out. Water, ammonia, nope. Let me try that again. Hydrogen fluoride. Okay, what is the most important intermolecular force in all three of these molecules? Yes, hydrogen bonding, correct. How many hydrogen bond donors do we have in water? 2. How many hydrogen bond acceptors do we have in water? 2. So I'm going to donor, 2, acceptor, 2. So each molecule here that can therefore participate in 4 hydrogen bonds, 2 as donor, 2 as acceptor. Okay. The ammonia, how many hydrogen bond donors do we have? 3. How many hydrogen bond acceptors do we have? 1. Now, once the acceptor, if you think about a sample that is pure ammonia, and you count up how many hydrogen bond donors in the entire sample, say you've got a mole of ammonia molecules, you have a mole of hydrogen bond acceptors. And it doesn't matter that you have 3 moles of hydrogen bond donors, there aren't enough acceptors to use all of them, right? So here you're only going to have half of the amount of hydrogen bonding as you have in the case of water, right? Hydrogen fluoride. How many hydrogen bond donors do we have? 1. How many hydrogen bond acceptors do we have? 3. So we have exactly the same argument, it's just swapped because you run out of donors and can't use all the acceptors. So again, this one you only have half as much hydrogen bonding as you do in water. So that is why water has a higher boiling point than both of these two. Yes?
So if ammonia and hydrogen fluoride were to make a solution together,
Yeah, I would think so. If you made an equimolar mixture of ammonia and hydrogen fluoride, then that would have a lot of hydrogen bonding. Yes, that would be great. Okay, so did that one. Okay, there was some confusion about one of the quiz questions in the video, which noble gas has the strongest dipoles? Remember that the way that question was worded asked for the noble gas that was group 6 or above, or sorry, period 6 or above. Period 6 is this one, and by above, I meant above on the periodic table, not as in larger number, okay? So based, what kinds of intermolecular forces do we have in the noble gases? Dispersion forces, London dispersion forces, that's right. Do dispersion forces get stronger or weaker as you go down a group? Stronger. So what's the answer to this question? Radon. Okay. And the reason I say group period 6 or above is that this OG thing, you don't make nobody's made a large enough sample of it to actually make this any kind of measurement on it. So, okay, done with that. All right, I want to come back now. We did that one. Last one we had here got 8 upvotes. Number of phases present in milk, and I posted an announcement about this on Piazza. I made a mistake in the quiz, and the quiz, the question states, in milk, it's a colloidal suspension of fatty microdroplets in an aqueous solution. How many phases are present? Well, the microdroplets are a phase, and the aqueous solution is a phase, so it should have been 2. And I apparently clicked the wrong thing in the video, and 0 is what it's counting as correct. So know that the answer is 2, but enter 0 so you get the points. Okay. I would love to go back and correct it, but I would have to delete the video, re-upload it, and everybody that's already taken the quiz would have to redo it. And people are having enough trouble with them already. I don't want to have to force people through that. Okay, so I think I have now gone through all of the muddiest point questions that came up on Piazza. So we have about 10 minutes left in class. I will take any questions you have here in the class or from people in the chat. Yes. A question about what and how it relates to boiling point? Elevation, okay. Sure, okay, so the question is, how does elevation relate to boiling point? So the first thing to ask is, what do we mean by boiling point? Can somebody give me a definition of boiling point? Yes. Okay, the heat it takes for a gas to escape the liquid. Okay, how do people, there's certainly boiling is the process of gas escaping the liquid. Is the boiling point the amount of heat it takes to do that? Yeah. It's what? The energy? Well, energy and heat is an energy transfer. Okay. You're on the right track here. When the pressure of the in the liquid equals the pressure of the outside atmosphere. But let's get back to the question of whether this is a heat, the boiling point is a heat or not. Anybody have a thought on this? Yes? It's the energy. So if I say the boiling point of water at 1 atmosphere pressure is 25 kilojoules, is that how we identify a boiling point? No. What type of quantity? What type of units would we use to identify a boiling point? Can't hear you. I don't know who's talking. Celsius. So it's a temperature. A boiling point is a temperature at which something happens. And it is the temperature at which the vapor pressure of the liquid equals the atmospheric pressure. So if we were to plot vapor pressure of the liquid as a function of temperature, you're going to get some kind of curve that looks like this. Okay? And at some point, at some temperature, this is going to end up being the external atmospheric pressure. Okay. Now, why does that matter? Why is this relationship what we call boiling? Yes. Right, it has to do with bubble formation. So if we imagine having a beaker of a liquid that we can heat from below, and imagine that some of the molecules down here in the middle spontaneously, through collisions with their neighbors, get enough energy to form a small bubble. Okay? Well, we can determine from this plot right here what the pressure within that bubble is of just the pure vapor. So if we're down here and we have this pressure and it's below the atmospheric pressure, that means you have this huge pressure being applied on top here and only a tiny little pressure pushing outwards from this bubble. So what will the bubble do? It'll collapse. So that is not boiling. But when you heat it up further, move the temperature over to this point, and now one of these bubbles spontaneously forms, and the internal pressure is now equal to the atmospheric pressure. At that point, the bubble is stable because the external pressure and the internal pressure are the same, and so no net pressure difference means there's no force causing the bubble walls to either go in or out, right? And so, but the bubble now is less dense than the material it's surrounded by, and so the bubble floats to the top and breaks. That is boiling. So the boiling point is the temperature at which the vapor pressure of the liquid equals the atmospheric pressure. Now, let's relate this now to the altitude question. What is the atmospheric pressure on the top of Mount Heinemann compared to here in Boise? Is it higher or lower? Lower. The pressure's lower because the atmosphere gets less dense as you go further out from the Earth. Okay? So if the atmospheric pressure is lower, what does that do to the boiling point? It's lower. And so at a higher altitude, liquids will boil at a lower temperature. Okay, Does that make some sense? All right, was there something from the chat?
There's two. So the first one is, can you please clarify if there's a difference between intermolecular forces and intermolecular attraction?
Okay. Clarifying whether there's a difference between intermolecular forces and intermolecular attractions. So, not really. I mean, there are some kinds of intermolecular forces that are repulsive, but really the only one of that is going to be ion-ion interactions where it's the same charge. Okay, or the repulsion that's felt by a dipole towards an ion or dipole of the same charge on that. But I tended to use them interchangeably because the repulsions tend to not matter too much, whereas the attractions do end up mattering quite a bit. So there is a little bit of a difference, but it's not a distinction that is really worth worrying about. Okay, and you said there were two?
So the second one is, can you explain the difference between charges such as ion, dipole, and induced dipole?
So explain the difference between
Charges such as ion, dipole, and induced dipole.
Okay. So explain the difference of the charges here. So the charges for an ion are simply, you have two separate species, and one of them has stolen electrons from the other one. Okay. So one molecular component has a permanent charge that is either positive or negative in units of whole electrons. The other one has whichever one I didn't already say, I don't remember if I said positive or negative, has the other charge. So ions are fully charged. Dipoles are charge separation within a single molecule, so that you have a partially negative end and a partially positive end, less than usually a full charge. That is nonetheless a permanent separation of charge rather than a fluctuating one. Induced dipoles are a result of fluctuating charges. And so if you have an electron cloud that then responds to a neighboring charge or dipole or induced dipole, then that neighboring charge dipole or induced dipole can cause a slight shift in the electron positions, which results in a dipole. Okay. All right, we've got about 2 or 3 minutes left. Anything else? All right, there were some very good questions today. I really appreciated that. Thank you all. No. So, a follow-up question was, are induced dipoles always in nonpolar molecules? No. An induced dipole can exist in anything that has electrons.